Okay, welcome to this video, and in this video we're going to talk about PCA, Principal Component Analysis. Okay, so what is PCA? PCA is a technique in machine learning for dimensionality reduction, for reducing the dimension. Okay, so to motivate this, I have this example over here. So we have a 2D example, and you can see that the data points lies approximately onto this line. It means we can project the data points onto this line and make it one-dimensional. We can reduce the dimension. Okay, so a question in your mind might be why we want to project it onto this line, meaning let's say onto this vector. We want to project the data set onto this vector. Why do we want to do that? Why we don't project it onto the perpendicular vector? And the answer to this is we want to project it such that the variance is the highest. Okay, so such that we have the highest variance. And we can see that if we project it onto this line, then we're going to have the highest variance. Why are we going to have the highest variance? Because this much is the variability. You can just see by visual inspection that the variability is highest, but if you project it into this line, then this will be only onto this much space, the variability is low. So this is the reason why you want to project onto this line. Okay, so this thing, what I've written here is the projection of the data points onto W. So this is W transpose Xi W. This is the mean of the projections, W transpose Xi bar W. Okay, mean is linear, so you can write it as this. We want to find the mean of the individual unprojected data points, and then do this W transpose Xi W. This will be the mean. Okay, and now let's go to another page and let's do what you want to do next. We want to maximize the variance, so we have the projected data point as Xi transpose, okay, maybe W transpose Xi W. This is the projection of the data point onto the vector W, and the mean is W transpose Xi bar W. This is the mean of the projections. This is the mean of the projections. Okay, and the variance here is going to be 1 by n, or maybe n minus 1, or maybe n. Okay, it doesn't matter too much. Do you prefer 1 minus n or n? Okay, so 1 by n, sum over I is equal to 1 to n. And the magnitude of this, which is going to be W transpose Xi, so the magnitude of the data points minus the magnitude of the mean, W transpose Xi bar whole squared. This is going to be the variance. Okay, and we want to maximize this. We want to maximize this thing. We want to maximize the variance. Is this visible in the camera? Okay, so how you go about maximizing it? So the next step towards solving it is we're going to factor out. We are going to factor out W transpose from this. So we factor out W transpose. It is going to be W transpose Xi minus Xi Xi bar, and this whole thing whole squared. This whole squared. Okay. Alright, so next, so the square of this thing, so this is the same thing as I can write this thing as W transpose Xi minus X bar, this thing, and the same thing multiplied. So the same thing multiplied here that we have is W transpose Xi minus X bar. Okay, good. Now furthermore, the next that we can do is we can write this as W transpose Xi minus X bar, and we can do one thing. We can change this to Xi minus Xi transpose W. It's the same thing. You can write this as this. Okay, it's the same thing. And now what you can see here is that these W's, okay, are independent of the data points. So you can make this come out of the summation sign. So this will be W transpose times 1 by n sum over I is equal to 1 to n, and xi minus x bar times xi minus x bar, and this whole thing times this w, those two w comes out of the summation sign. And what is this thing? What is this 1 by n w? What is this thing? This thing is the covariance matrix. I cannot write this comfortably here, so it's better here. So what was this thing? Is the covariance matrix. Okay, C. Let's denote this by C. So this is going to be W transpose CW. This is the variance. This whole thing is the variance. W transpose CW is nothing but the variance, and we want to maximize the variance. Okay, that's why that is our goal. So our modified goal is max over W of W transpose CW, and we already know that W is a unit vector, so W transpose such that W transpose CW is 1. Okay, this is the objective function that we want to maximize. Okay, so let's you need to be familiar with Lagrange multipliers. So we're gonna create Lagrange function out of this, which is going to be W transpose CW plus lambda times 1 minus W transpose CW. Okay, so you can take the derivative of this with respect to W. You can take the derivative of L, this L, with respect to W, and what you're gonna get is we're gonna get dW. Is this visible? dW by dl by dW. What a silly mistake. dl by dW. So this is L. So dl by dW, we're gonna take the derivative with respect to W of this. Okay, so let me just write this whole thing again here, so that you also can take derivative along with me. Okay, this is the thing, and we want to take the derivative of this. This is the Lagrange. We want to take the derivative of this dl by dw. Okay, what is this going to be? This is going to be 2cw plus. Okay, so this is the negative sign, so it's going to be changed into negative. Negative. Okay, it shouldn't be w. Wait a minute. It shouldn't be w transpose c. It should be w transpose w only, because it's the magnitude. Oh, silly mistake. It should be w transpose w only. Same change here. W transpose w. So yeah. So this will be 2 lambda w. Okay, so we came to this step, that the derivative is going to be 2c w minus 2 lambda w. And you want to maximize this, so we're gonna set it to 0. So 2cw minus 2 lambda w equals 0. So 2 to cancels out, and we're gonna have cw is equal to lambda w. Okay, and by looking at this equation here, this is the same eigenvalue equation. C is the matrix, W is eigenvector, lambda is eigenvalue, and you can, by glaring at it, looking at it, you can see that W is the eigenvector and lambda is the eigenvalue of the matrix C. Okay, and the lambda is the solution to this, and the lambda that we get is the eigenvalue of C. Okay, so there will be many lambdas there, and which lambda you're gonna pick? Which eigenvalue you're going to pick? Okay, to answer that, let's multiply W transpose to the left of this. So this is going to be W transpose CW times lambda W transpose W, and this thing is 1. So this is going to be W transpose CW is equal to lambda. Okay, and so the lambda, this is our goal, and the goal, the solution to this goal is the lambda, and the lambda the solution lambda is the eigenvalue of the covariance matrix C. Okay, and the covariance matrix C is same as W transpose CW. Okay, the covariance matrix, I'm sorry, the eigenvalue of the covariance matrix is same thing as W transpose CW. This is the variance, and lambda is our variance. Lambda is also our variance. So which lambda do you pick? You pick the highest lambda, okay, highest lambda, because it has the maximum variance. Okay, and the vector corresponding to the highest lambda is going to be your principal component onto which you're going to project the data. Okay, so you're going to project the w. The w is the eigenvector that we're going to project the data onto. Okay, this is the w that you're already interested in. So w is the, let me just summarize this here. So w is what here? W is the eigenvector of C corresponding to W is the eigenvector of C corresponding to highest eigenvalue lambda. Okay, so W is the eigenvector of C corresponding to highest eigenvalue lambda. But we're not gonna, in general, we're not gonna pick only one lambda. We're gonna pick as many lambda as needed. Okay, so let's say we want to cover 95% of variance. So you're gonna pick as many lambdas which gets you 95% variance. Okay, so how do you calculate that? You're going to write the first lambda, you're going to write the second lambda, take the second lambda, you're going to add it to, let's say, k many lambdas, and you're going to divide it by all the lambdas that you have, all the lambdas, and if this is 95%, let's say 0.9, if you want to cover 95% of, in general we do cover 90 or 95% of the variance, then you're gonna pick that many of lambda, and you're going to project onto that many eigen vectors, the principal components w. Okay, so the rule of thumb is we're going to pick let's say how many lambda, as many lambda required to cover, let's say 95% of variance, and you're gonna pick that many lambdas, the variance, and you're gonna pick and that many eigenvectors, okay, the w's, the principal components of the covariance matrix, okay, and you're gonna project it onto them. So this was a lot of math here, and in summary, let me just summarize this. Let me just summarize what are the steps that we have come up with. So the first thing is center the data, because to find the covariance matrix we have to center it. Okay, so this is the center the data, or maybe you can start with just finding the covariance. Okay, because in the covariance part we just center it. Find the covariance matrix. Find the covariance matrix. How do you find the covariance matrix? You find the covariance matrix of the data by doing this: 1 over n sum over I is equal to 1 to n xi minus x bar transpose. Okay, so xi minus x bar times xi minus x bar transpose. This is how I find the covariance matrix. In matrix notation, let's say this x, the capital X, is our centered data set. Then the covariance matrix C becomes 1 by n x transpose. Okay, so it becomes this 1 by n x transpose. So this part will be the x centering, and this will be x transpose. So find the covariance matrix, this thing. And the second step after finding the covariance matrix is that we look at here. The next step is we find the lambda, which is the eigen value of the covariance matrix. Eigen values of C. We find the eigenvalues of the covariance matrix. Lambda 1 to lambda n. We're gonna pick as many lambda as required, which covers as much variance as we want. Let's say k many lambdas, we pick k many lambda we pick, and we want to pick in descending order. Lambda 1 will be the highest eigenvalue, lambda 2 is going to be the second highest, and lambda k is going to be the smallest eigenvalue. Okay, and in the same order we're going to pick up the eigenvectors of C. Okay, we're going to pick up the eigenvectors of C. Okay, so you're going to calculate the eigenvalues and eigenvectors of C, and the third will be to project the data points, project data points on the eigenvectors, let's say principal components, PCs W. These are principal component PCs. The same PCs are, or the principal components are the eigenvectors of C. Okay, so project the data points on the principal components, and that's it. This is the steps of principal component analysis, only these 3 steps, and this is the summary of principal component analysis. And I hope you have liked this video.